Hello everyone, today we're going to be talking about the musculoskeletal system and a little bit of the anatomy and physiology that I've learned as a student physical therapist, as well as my journey studying the CSCS. So essentially, what is the musculoskeletal system? It allows you to move, right? So it's composed of muscle tissue, bone, connective tissue, and those are pretty much the main parts, along with the nervous system. And my goal today is to give you some of the value, like how does this apply to your life and how does your body work, and also how can we optimize these tissues and make sure they function properly over our lifespan. So first of all, muscle. What is skeletal muscle? It is one of three types, right? You have cardiac muscle fibers, you have smooth muscle fibers. The smooth muscle fibers are found in your veins and your organs, but today we're going to be focusing on skeletal muscle fibers because this is how we move. Our joints, we typically think of multi-nucleated, long, cylindrical skeletal muscle fibers as the musculoskeletal system. So you can think about muscle as kind of like a bundle of sticks. So the functional unit is a muscle fiber, also known as a muscle cell or a myocyte. And if you hear me saying prefixes like myo just means muscle, same as sarco. Sarco and myo are both muscle in Latin and Greek. So yeah, you got myocytes, you got muscle fibers, and these guys are surrounded by connective tissue. So you have a muscle fiber surrounded by endomysium, which is like the connective tissue, and then a bundle of those is called the fascicle, and I think in Latin that is a bundle of sticks. So just a bundle of muscle cells. And what's cool and unique about muscle cells, like a ton of things, people typically think that skin is the largest organ, but I think by body mass, it's actually skeletal muscle. And muscle fibers can actually be the width of a human hair, which is huge. Like the diameter is huge for just a cell, because we typically think of cells as microscopic. But if I were to hold up a cell in front of the camera, you could definitely see a single muscle fiber, which is incredible. Additionally, muscle cells can run the entire length of a muscle. This is not always the case, but if you think about like your sartorius, which runs from your hip to your knee or your femur, it would be almost a foot and a half, depending on the length of your femur or that muscle, and that's a very long cell. So that's why there's a lot of nuclei, and that's just one of the cool things about muscle cells. And muscle fibers, to make it even more simple, come in a lot of varieties. So you have slow and fast twitch fibers. So if you think about your type 1s being your slow twitch or slow oxidative, these guys you can think about marathon runners who need a low power output over a extremely long time. And we have to first get into kind of the physiology of how muscle cells utilize energy and that kind of thing. So type 1s have a ton of mitochondria and aerobic enzymes. And aerobic basically means like you're using oxygen to produce energy. And mitochondria produces things like ATP through the Krebs cycle using oxygen. So marathon runners use type 1s like in their soleus, and they can do this because of those mitochondria. So tissue uses more myoglobin, which is the same as hemoglobin, but it's muscle. So myoglobin, the red pigment, and that's why people also say type 1 fibers are the red fibers, or type 2 fibers are the white fibers. Because of that, they heavily use oxygen, and to use oxygen, you need heme or myoglobin to store that oxygen for use. And the type 1 fibers, you can think of this like in the calf muscle, the triceps surae. So the gastrocnemius is the big superficial calf muscle that is used for sprinting because it's a higher proportion of type 2 fast twitch muscle fibers. And the soleus is the thinner fish-shaped muscle close to your heel cord. It's also part of the triceps surae, but it's almost 80-90% slow twitch fibers. So moving on to the type 2X, you can think about these as like the 40-meter sprinters because they almost exclusively use anaerobic glycolysis for their energy, so they do not use oxygen. And because of this, their fiber color is white because of that low glycogen content. Also, they have the largest diameter. So if you're optimizing for a huge amount of force under a very small amount of time comparatively to type 1s. And in between these, we have type 2A, which is kind of like the intermediate fiber. So if you can imagine somebody who needs to run 800 meters. So it's not quite a 40-meter sprint. It's not quite 23 miles, but it's 800 meters. So you need an intermediate so it's a fast twitch muscle, but it's also oxidative. So they have a higher concentration of mitochondria than the type 2Xs because they use oxygen, and they can be aerobic, but they're not quite slow twitch. So they produce more force, they're more fatigue resistant, they have more capillaries than the 2Xs, but they're not quite the 2As. They're not quite the 2Xs or the slow twitch. They're kind of intermediate in between. And the reason this is important is because when we train any component of our body system, we have to think about the specificity of our training. So if you want to be a sprinter, you want to adapt the 2A fibers and the 2X fibers to be able to produce hypertrophy, and hyper just means more, and trophy is growth, so more growth of muscle. Hypertrophy for specificity, we want to increase that fiber size, and this can be done with a specific program. And if we want to increase, say, the mitochondria concentration and the capillary density around our slow twitch muscles like our soleus, if we want to train sprinting, then we're going to do activities specifically for that adaptation. So for instance, if you want to increase your mile time, then you would be doing thresholds. So a mile time would be like holding X pace for a mile. And this would probably adapt your mitochondria in the slow twitch muscles, but it would also be adapting the fast twitch fibers at the beginning, and for sure the intermediate fibers, because you need oxygen to run a mile, because you cannot do that only anaerobically without oxygen, but you also need those intermediates. So you need some mitochondria adaptation. That's kind of what I'm talking about with the specificity principle. And then there's specificity and also progressive overload. So for training for a marathon, we want to have our long runs, and to overload that, I prefer to do that with distance in our long runs, not necessarily speed-wise, but with volume-wise, because we are adapting the mitochondria, the aerobic enzymes inside of those specific type 1 muscle fibers. So I know that's kind of a lot of jargon, but I hope you got something from that. And another thing we can think about is how athletes can improve their muscle force production. And this is kind of getting back to that specificity. So now we are optimizing for force production. So to increase the amount of force we can produce, we need to first incorporate heavier loads into our training to optimize that neural recruitment. We'll get a little bit into that when we go over the nervous system. Also, increasing the surface area of the muscle. So by hypertrophying your bicep, you're going to increase the volume of muscle cells, and with that comes more interaction between actin and myosin, which has more tension and more force resulting from that. And how do we do that? We need to perform multi-muscle, multi-joint exercises with power. And power is basically force and speed combined, and this will optimize that fast twitch muscle recruitment. So if you can think about deadlifting for force production, it doesn't necessarily need to be a fast movement. It just needs to be a very strong movement. So deadlifting, it doesn't matter how powerful it is, because power is incorporating speed as well as force. So if we just want to improve force production, we would do something like a 5-rep deadlift, which means like 3 to 5 repetitions of a heavy lift to hypertrophy and also to increase the neural recruitment of those type 2X fibers. And moving on, this might help you understand the physiology of the skeletal muscle. So mitochondria, of course, as we know from middle school, are the powerhouse of the cell. And what that means is they supply ATP, or energy, for the movement of our body, right? And this is completely done aerobically with a higher concentration of type 1 slow twitch fibers, because they're more aerobic than the 2X and 2As. And an important adaptation to endurance training is we can actually increase our cellular mitochondria, which is very cool because, obviously most of your physiology is set for you when you're born, but it has been shown that you can increase your concentration of capillary density and also your cellular mitochondria. So depending on what you want to achieve with your life, you can train that system. And during a rest period between sets, you use your mitochondria, even if you're doing an anaerobic strength-based workout, like that 3 to 5 sets of deadlifts that we were talking about earlier. That's mostly anaerobic. So it uses glycolysis, it uses creatine phosphate to produce energy. But between sets, so you take a 3 to 5 minute rest period, and the reason you do that is so that you can use your mitochondria to produce ATP in the myoglobin. So when you go for that next set of heavy deadlifts, you have ATP stored. And this is why it's so important for you to think about how long your rest periods are and to perform deep nasal breathing to optimize that recovery of that ATP so you can optimize your performance every set. And moving on from mitochondria, we have myofilament. So the myocyte is the muscle cell, and the muscle cell is composed of many filaments like myosin and actin. And these two filaments are how muscle contraction can occur. So if you can think about like a thick myosin filament is kind of like a guy pulling a rope, and the actin is the rope. So with a muscle contraction, the myosin will attach to the actin and pull. And that's happening hundreds of thousands of times a second. There's a ton of these guys, and we'll get into how that actually occurs. But basically those two myofilaments, actin and myosin, crossing over each other is how skeletal muscle contracts and shortens. And that's basically how you can maintain tension in a muscle, and that's how you produce force and you move your joints. So we will use myofilament anatomy later, but moving on to sarcoplasmic reticulum. I know that's a big word, but you just break it down. So sarco is muscle, plasm is, I think that's the inside of a muscle cell. I'm actually not sure what reticulum is, but they are parallel to the myofibrils, which, muscle cells, and they function to store calcium. And we'll get into why calcium is super important for muscle cell contraction, but without calcium, you can't contract your muscles. And the enlarged areas around that sarcoplasmic reticulum are the terminal cisternae, and they're actually part of the sarcoplasmic reticulum, but they release the calcium into the muscle fiber to allow for that contraction to occur. And moving on to an action potential, these are electrical signals that's coming from your brain to your muscle cell. So if you can imagine trying to lift a ball off the ground, you're going to think about that consciously. That's going to go through your motor cortex. It's going to go down through a few pathways, but you need to think about an action potential being that electrical signal from your brain to your muscle that says, hey, let's contract. In that action potential is what's going to unlock that calcium in that terminal cisternae. And we're going to use ATP to pump the calcium out of that cell back into the sarcoplasmic reticulum, and that's going to allow the muscle cell to relax. And I guess a cool way to understand this is rigor mortis. If you've heard about someone who dies and their muscle cells seize up, they can't relax. This is because the sarcoplasmic reticulum, which stores the calcium after death, they empty their calcium into the muscle cell, and because there's no more ATP to pump the calcium out of the muscle cell, all of the muscle fibers are contracted, and they can't relax without the pump, so they stay contracted. So that's kind of cool way to think about the physiology. Also, caffeine, you might have heard, is a very good performance enhancing drug because it can make skeletal muscle more sensitive to action potentials, and it can also make cardiac tissue more sensitive to calcium, and that's why caffeine can actually increase your heart rate. So just things to think about. I think that's pretty cool. But moving on from the sarcoplasmic reticulum, we have the T-tubules, and these are why your muscle cells contract as a unit and not alone. So if you contract your bicep, the whole thing lights up at the same time, and it's because of these T-tubules. And what they are essentially is just little tunnels that go into your muscle, the belly of your muscle, and when the action potential hits that membrane around your muscle, it goes into the muscle as well, so that all of your muscle cells get the message from your brain at the same time, and they contract in unison. And they discharge the action potential basically as an electrical signal, and then that turns into a chemical signal with acetylcholine, and that's at the neuromuscular junction. But that's all you need to know for that. Also, proprioception. So this is how we sense our environment. And you can think of that kind of like nerves. So if you feel your feet are on the ground, where does your foot feel the pressure? Or if you've ever heard of someone say, think about where your tongue is in your mouth, that is proprioception. That's your awareness of where your body is in space and the environment. So proprioceptors are also in your joints, they're in your muscles, they're in your tendons. So this is why we're discussing it. So you have efferent information that comes from your brain to your muscle to consciously act something out. But you also have afferent information from your senses to your brain. So it's like when you touch a hot stove, that's afferent information. Oh my God, that's hot. Pull away. That is an afferent information reflex. So that's important because we have these things called Golgi tendon organs. And these are located in the tendon near like the myotendon junction. So why this is important is these are composed of extrafusal muscle fibers. So when the tendon is stretched and it feels tension, like when you're stretching your calf muscle or your quad muscle, if it's too much, the GTOs will communicate with your like an inhibitory neuron in your nervous system to relax that muscle, to avoid the rupture of the tendon or the muscle. And the reason I'm bringing this up is because the GTOs can be overloaded. So this is what we're actually doing when we're weight training, is learning how to handle heavier loads and saying, actually GTOs, I got this. Like I can handle this amount of weight. We're not going to tear, so you can turn off. But also we can do that through stretching. So GTOs, if you ever heard of you should stretch your muscle for 15 seconds, in part that number comes from overloading GTOs. So GTOs take at least 6 seconds to overload and relax, which is why static stretching should be performed at least 10 seconds continuously, so we can make sure that GTO is overloaded and we get the resulting flexibility that we're training for. And moving on from GTOs is muscle spindles. So these are a little bit different. And when I was talking about that hot stove reflex, this is kind of how that happens. So you have proprioceptors. So these are, I think, intrafusal muscle fibers, but when they're stretched, your brain kind of freaks out and says, hey, if we're lifting a very heavy weight, we need more motor recruitment. And how do you get that? You have more action potentials from your brain to your muscle to have a stronger contraction. So when the physical therapist or the doctor taps your knee tendon with a hammer, your muscle fiber deforms and your muscle spindle says, hey, we have this deformation here. I'm scared of tearing, so I'm going to contract that quad muscle to resist the deformation. So that's how that knee tap reflex works, is these little muscle spindle proprioceptors you have in your body. And finally, the last thing that's cool about skeletal muscle is it also helps your cardiovascular system. So your calf muscles are pretty far down in your body. It has to fight gravity. And part of what helps the blood return to your heart is what's called the skeletal muscle pump. So when muscle contracts, it moves the blood in the veins and the arteries, and it squeezes that tube of the vein back to the heart. And the way this happens without what's called retrograde flow is there's one-way valves that prevents that backflow into your toes. So that makes, when you contract your muscle, it just shoots it back up, and then gravity is stopped by one-way valves, or it's not stopped, but the backflow is stopped by the valves. And this is how, in part, when you work out, your cardiac output increases so much, because when you're running, if you think about all of the skeletal muscle contractions that are happening all around your body, you're squeezing, you're pumping your arms, you're pumping your calves, obviously. All of that returns blood at a faster rate. So lastly, we have connective tissue. Well, second to last, we have bands of connective tissue wrap around the endomysium, paramysium, and endomysium, wrapping around the muscle belly itself. And it's kind of cool because the endomysium runs throughout the fascicle, or around each muscle fiber, and they connect at the tendon. So the endomysium, the paramysium, and the epimysium, they kind of run all through the muscle. So when you contract, there's an even tension through the muscle. And those connective tissues form the tendon. So that's pretty much all I have about CT. It's incredibly important. Maybe we'll have another episode specifically on it later, but I'd like to move on to bone. And this is an incredibly important system, because if you could imagine not having bones and being a blob of, soft tissue, it would be pretty hard to survive. So what do? They protect your organs, they produce blood cells, your marrow, and they also allow for mobility. Because when your skeletal muscle contracts, how do you move that joint? So your skeletal muscle contracts, that contraction force goes through your connective tissue, and the connective tissue reaches that bone. And pulling on the bone is what actually moves the joint. So what is bone made of? It's mostly collagen, which is code for protein, and that serves as the foundation for bone, and it gives it its tensile strength. But bone is also composed of calcium phosphate, which makes it very hard, and it allows it to resist compressive forces. So when we want to think about increasing bone mineral density and avoiding things like osteopenia, which is the beginnings of osteoporosis, and what osteoporosis is, it's in the name. So osteo is bone, and porosis is pore. So if you can imagine looking under a microscope and seeing just a bunch of tiny little pores through your bone, that's not what we want. We want strong bone. But how do we get that? Well, we have to go back to the idea of specificity and progressive overload. And in this case, we have Wolff's Law. So this is the adaptation to impose demands. So when we want to increase the strength of a tissue, we need to impose the demands for that adaptation. So especially for young people, it's important to adapt our bones so we have an increase of bone mineral density. And what that means is we get as much adaptation in while we are so young. We can eat, we can produce enough protein synthesis, we can get those stress lines all the way through our bones to be hard and ready to, resist forces. Because when you get old and you don't eat well, you don't load your bones, you are way more at risk if you have osteoporosis for what's called fractures. So, there are people who are in their 80s or 90s, even 60s, who, when they sit down, can actually fracture their vertebra because the weight of gravity and the force, acceleration and gravity compressing the spine can cause a fracture because the bone mineral density is so weak, and it can't, So you get the point. But how are we going to improve the quality of our bone? So we need to eat enough calcium, first and foremost. I think, you can go on the FDA website for the, recommended intake. I think it's about 1,000 to 1,200 milligrams, and it's like milk, beans, and salmon are some examples of calcium. But if you're at risk, obviously go talk to your physician or a nutritionist or your healthcare provider so you can get the quality information you need. But this is just like for educational purposes. We also need to produce or make vitamin D3, and this is actually like 600 IU, which you can get in about 15 to 20 minutes with sun exposure, walking around with your arms exposed, that kind of thing. And foods high in D3 are like eggs and fish. And why is this important? It helps our body absorb and store calcium to improve that bone mineral density. And my favorite soapbox to stand on is protein. I personally eat about 1 gram per pound of body weight. However, like the RDA for this nutrient is like about 0.8 grams per kilogram, which is, in my opinion, fairly low. But do your own research, but I would recommend 1 gram per pound of body weight if you have no other health contraindications. And again, we need to resistance train to increase Wolff's Law, which then is going to increase bone mineral density. So you can think about an astronaut floating in space. These young, healthy people go into space and they get sick because gravity is not there to impose Wolff's Law, to impose a load on the bones. So they come home and like deathly ill, and they lose a ton of bone mineral density. So that's why it's important to perform resistance training. ACSM, or the American College of Sports Medicine, recommends 2 to 3 days per week resistance training every muscle group. And if you're resistance training muscle, you're resistance training bone, because it's all connected. And finally, we get to the nervous system. So this is important because without the nervous system, your muscles would never contract, because they are essentially, your brain and your motor cortex is how you can think about voluntary contracting. Like with the patellar tendon reflex, when the physician taps your knee with the hammer, that is with an inner neuron, so you don't really need the brain. But moral of the story is nervous system, action potentials, that's how your skeletal muscle contracts. And this communication happens with motor units. You might have heard about this, but what it is a motor neuron, and a motor neuron is innervating many muscle fibers. Um, if you can think about your quadriceps muscle, it's very strong, right? It's got a lot of force that it can produce. And because it's so gross in its movement, like it's not like your eye muscle or your hand muscle that's kind of like a fine motor movement, like writing your name would require very fine motor control. Your quad muscle, because of how huge it can innervate hundreds of thousands or hundreds to thousands of motor units with one, or motor neurons with one motor unit. But your eye muscles, for instance, they're very fine movements. If you can think about focusing on anything in the room, or if you're driving, don't focus on something. But it would almost innervate one individual fiber for every motor neuron. So that's kind of unique because it allows us to have specificity in our physiology, which is always important to understand. And why that's important is because when we have action potentials, they transmit down our motor units and the neurons like electricity in a charging cable. And that's pretty much how we communicate. Our brain sends signals all the way down through our nervous system, like a charging cable or like a phone cable that you see on the side of the road. And for this to occur normally, you need a few things. So I'm not going to get into neuroanatomy. I'm going to give you the basic understanding. So you have like we have the neuron and you have Schwann cells. And for that you need fat. So that's kind of like your insulation. So the electrical signal can go all the way through the cable with as minimal decrement as possible. So you need to consume fat, and you also need acetylcholine, which we've established is the neurotransmitter for muscle. And getting into the all or none principle, so all muscle fibers are innervated by that same motor unit, and that's how we can contract at the same time. So we have those tubules to communicate at the same time, but also you cannot selectively contract a single muscle fiber that's innervated by a motor unit. It's all or none. And another principle is the size principle. So smaller motor units will be recruited before larger motor units, and this might be intuitive. Like if you have a manual car, you can think about shifting gears progressively into more force production when it's needed. But this is also presents an issue for aging. So if you can imagine a 80-year-old who doesn't necessarily get into many fist fights or doesn't lift heavy weight, they don't ever recruit the larger muscle fibers. And the reason we talked about that type 1, type 2A, type 2X is because those are incremented in size. So if you can remember, 2X is the largest, type 1, slow twitch, is the smallest. So the type 1s are postural muscle, so they're always pretty much activated at a very low level, and so they don't really atrophy much with age. However, type 2Xs, the fast twitch muscle fibers, they atrophy because of the size principle. So if you never use the type 2X fast twitch muscles, your motor units communicate. They're like, hey, we haven't activated this guy for 10 years. Why do we need him to stick around? Because your muscle and your brain is intelligent. It wants to preserve as much energy as possible. So that's the size principle. If you want to train your muscle to produce more force, that's kind of what you're doing. It's called motor learning. So whenever you contract your muscle intentionally and you feel that tension in your muscle, you're using fast twitch muscle fibers because you improve the load. So you increase the load or you increase the speed. You're saying, hey, size principle, we need those big 2Xs. And so you're motor learning, you're learning how to contract those units. And that is cool because most people don't have access to all of their motor units because they haven't trained them. So most of the gains, most of the gains that you'll get initially are from motor learning. People tend to think about gains in the form of hypertrophy or the increase in muscle fiber size. That is possible, but in the first 4 weeks, it's mostly motor neuron learning. So this is why it's important to get the form right, so you can use the motor units correctly with the correct form and the correct posture, and hypertrophy will come later with consistency. And the junction between that neuron, the nerve cell, and the muscle fiber is called the motor end plate. And again, if you think about your brain throwing out an action potential signal, going down the electric cable that is the nerve cell to the chemical signal at the neuromuscular junction, that acetylcholine is going to interface with the cell, and that signal to the sarcolemma. And the sarcolemma is the membrane that wraps around the muscle cell. That's going to propagate the action potential through T-tubules, which we've talked about before. And acetylcholine is released when the action potential happens. So if you can think, why is this happening? It's because of calcium. And we're so close to talking about contraction, but nerve cells create those action potentials so that the nerve cell can communicate with the muscle cell and say, hey, we need more calcium to be released into the muscle cell. And one action potential will yield one twitch. And action potential frequency, which is how close together the action potentials fire, can cause many puffs of calcium to stack up within a muscle cell. And this will allow what's called summation. So if you just need to move a water bottle for a couple of seconds, you might get a couple of twitches, a couple of steady tension that's produced in your bicep and your hand muscles over a very short period of time. But if you need to hold a squat, so if you're doing a wall squat and you're sitting there at the bottom for 4 minutes, you're gonna go into what's called tetany. So you have action potentials summating so much that calcium is just floating around the cell constantly at max force production. Because it's what's demanded for that action. And here we are with the sliding filament theory. And this is kind of why we went over actin and myosin. So you get the action potential. Action potential will go and stimulate calcium to be released from that sarcoplasmic reticulum. And calcium, why it's so important. If you think about actin and myosin, so myosin again is the guy who's pulling on actin, and that's how the myofilaments will slide over each other. What's preventing that from happening at rest is troponin. And troponin moves tropomyosin, which essentially prevents actin and myosin from interacting. So calcium binds to that. It's the key that unlocks troponin, and it moves tropomyosin, which then allows the tug of war to begin. So imagine, the myosin head is interacting with the actin. It pulls it, it unlocks, and how does it unlock? It unlocks with ATP. ATP is how we reset myosin to get ready for what's called a power stroke. And this can occur as long as calcium is present. So you still need those action potentials, you still need those pulses to be present for muscle contraction to occur. Next is optimal length tension relationship. So the number of cross bridges that form between actin and myosin at any instant dictates how much force production can be produced in a muscle. So if you think about a elongated muscle, so if you're curling your biceps like some dumbbells and your elbow is completely straight rather, you can imagine over lengthening that muscle, the actin and myosin is going to be less likely to interact. But if you have the dumbbells at 90 degrees, or your elbow joint is going to be at 90 degrees, you have the actin and myosin at an optimal length tension relationship. And what that basically means is, how do you produce tension? It's with actin myosin cross bridges, the tug of war. So the more we can overlap the actin and myosin, the more surface area of actin myosin cross bridges we can have, the more force production we can produce. And that's the contraction phase. So what do we need? We need ATP. That's going to allow us to keep doing the cross bridge cycling, maintain the tension, and that's the basics of muscle physiology. So good job, guys. And before, we're going to talk about like how to produce more force. What do we need to produce force? So we need, again, to think about producing force. So we need actual potentials from our brain to our muscle. We need to increase the size recruitment of larger motor units. So we're going to go from type 2 or type 1 to type 2A to type 2X. So we're going to get larger and larger motor units, which have more and more actin and myosin surface area. And then we're going to completely activate the motor neuron pool, which is unavailable in most people. So motor learning is the acquisition of voluntary muscle contraction that's previously unavailable if you do not perform resistance training or train at all. So this is why it's incredibly important to follow ACSM's recommendations. So doing 2 to 3 days of hypertrophy training, or not hypertrophy training, but resistance training. And this is going to allow you to train these systems, like overload the GTOs, increase the motor learning, and also get hypertrophy. And depending on your goal set, you're going to adapt these physiological principles to whatever your goal is. If your goal is to dunk, then you're going to be focusing on power. You're going to be maybe a little bit of hypertrophy, a lot of motor learning, and then you're going to perform that skill training. If you want to run a marathon, what are you going to do? You're going to work on those type 1 slow twitch muscle fibers to get those, capillary adaptations, mitochondria adaptations, everything that comes along with that specific training. So I truly hope you learned something today, and this was episode 1 of the physiology of exercise. Let me know what you think in the comments, like, follow, subscribe, and I'll see you all in the next one. Peace.